Hello everyone. Today we are going to study the geometrical properties of this section, that is the third unit of your strength of materials, that is form. Okay, we'll first understand the basic terms in the geometrical properties of the sections, then we'll go into deep about the properties of the geometrical sections. First one is center of gravity. Okay, so center of gravity of a body is a point through which the whole weight of the body acts. Okay, we say right that uh, at which the body has some point where if we make the body to rest over that point, then it will balance itself properly, right? So that point where the whole weight is transferred or acts, that point is called as the center of gravity. Okay, and it is represented by as represented by Cg or G, simply as G. Okay, the point where whole weight of the body acts, that point is called as center of gravity. Okay, the next is centroid, the point at which the total area of the plane figure is assumed to be concentrated. Okay, this is known as centroid of that area, and the centroid is also represented by Cg or G, and the center of gravity and centroid lie at the same point of that plane or object or a body. Okay, it might be object, it might be body or a plane lamina, anything it might be, but the center of gravity and the centroid lie at exactly at the same point. Okay, next is we'll try to find out the various uh, centroidal distance. Okay, how to calculate the centroidal distance of various regular shapes. Okay, that we are going to use in a day-to-day engineering life. Okay, it is first in the square or the rectangle. It is what is the total depth of the uh, rectangle, half the depth of it will give you at which the centroid or the center of gravity acts. It might be b by 2 or d by 2. It depends upon the how the rectangular is positioned. If it is positioned along the depth, then it becomes d by 2. If it is positioned along the width, then it is b by 2. Okay, next is triangular. Okay, for triangle it is h by 3 from the base. Okay, it's h by 3 from the base. It's if this is a triangle. Okay, when you measure from the base h by 3, okay, it is h by 3, and when you measure from the vertex or the apex, it is 2 by 3h. Okay, next is trapezoid, trapezium. Here is the formula: b is the bottom width and a is the top width. So b plus 2a by b plus a into h raised to 3 by 2 from the base. This formula will help you to find out the center of gravity with the reference or with the help of the base. Okay, from the base you are going to measure the center of gravity. Next is circle, that is the diameter divided by 2, because the diameter of the circle remains constant from any position of the circle or any point from the circumference of the circle. So it is d by 2. Semicircle, it is 4r by 3 pi. R is a radius, okay, from the base of the semicircle. Quarter circle is, the formula remains same, 4r by 3 pi from the base. Okay, these are the some of the regular shapes whose centroids are being found out, and remember these centroidal distance will be helpful for the solutions of the problem. Okay, next. So next is moment of inertia. So what is moment of inertia? We'll understand first. Okay, if you consider a body like this, okay, you consider a axis x and y. Okay, now when you want to find out the moment of inertia, means the area, okay, area of this body, okay, into the centroidal distance from that axis, if you call it as h, square of it, the area of the body, okay, plus or the product of, okay, into the square of the distance, okay, of the center of gravity of the area from that of the axis. Understand what I'm saying? If this is your area, okay, the center of gravity of that area to the distance from to the distance between the axis, that distance square will give you the moment of inertia. Understanding what I'm saying? The moment of inertia of an area and mass about an axis is the product of the area and the square of the distance of the 70 center of gravity of area from that axis. This is what I have explained previously with the help of the diagram. Okay, so the moment of inertia of an area, okay, what happens is, why this is necessary, the moment of inertia is necessary because some of the bodies, as you said, uh, it is very easy to find out the center of gravity, right? Because they are of regular shapes. When it comes to irregular shapes, it becomes very difficult to find out the moment of inertia or the center of gravity. So to calculate the center of gravity, this moment of inertia is required. Okay, that is the use of it. Okay, next is moment of inertia of an area about the x-axis. If this is an axis and this is your body, this is x, this is y. About this axis, if you are calculating the moment of inertia, then it is called as ixx. Okay, and if you are calculating the moment of inertia with respect to this axis, that is y axis, then it is called as iyy. Okay, if the moment of inertia is calculated, okay, about its own centroidal axis, okay, own centroidal axis, then it is called as ig. Why it is called g? Because we represent centroid or the center of gravity as g or cg, so it is ig. When we can write ig, when your object is of regular shape, then only we can say that it is the we can denote that moment of inertia as ig, because we can find out the moment of inertia of such bodies, okay, about its centroid. If it is irregular shape, okay, if it is irregular shape like this, we don't know where the centroid will lie. So to find out, what we'll do is we'll take an external axis with that reference of axis, suppose a and b, okay, then with the help of that axis we'll find out the moment of inertia. So that time we call it as a iab. Okay, that is what we call in case of irregular shapes. Okay, and the moment of inertia is in the SI unit as mm raised to 4. Okay, is mm raised to 4. Next is theory of parallel axis. Theorem of parallel axis. In this case, in this theorem of parallel axis, it is stating that, as I stated before, if there is an irregular body, as it is shown in this figure, okay, for that to calculate its moment of inertia, okay, so we have to multiply the area to the distance, square of distance from the axis, okay, plus the moment of inertia about its own centroid, okay, then we'll get the moment of inertia of that body with respect to the uh, external reference point, okay. As you can see here, we are calculating IB where the reference line is outside the body, okay, where we want to calculate the moment of inertia of it with respect to this AB line, right. That time the moment of inertia of that body with respect to the centroid, okay, plus plus the area of the body into the square distance between the centroid to the axis. That distance h is squared double times. That is what this theorem is trying to explain. Moment of inertia of the lamina about an axis in the plane of the lamina is equal to, it is saying that the moment of inertia of the lamina about any axis in a plane of a lamina is equal to the sum of moment of inertia of that lamina about the centroid axis is parallel to the given axis. Okay, we are summing up the moment of inertia of that lamina about the centroidal axis parallel to the given axis, and the product of the area of the lamina and the square of the perpendicular distance between the two axes. This is your first axis, and second axis is this AB axis. The perpendicular distance is this, right? That is h. That distance it is saying. Okay, so it is the formula like this. Whenever there is an irregular formula object or something different, the combination of two or three shapes, okay, that time you are going to go through this formula and you are going to set a separate reference line to it, okay. The theory of mutually perpendicular axis. If you take a body, okay, in a plane where two axes meet at the centroid, it is compulsory that these two axes should meet at the centroid of an object, okay. It should meet at the centroid of the object and they should be mutually perpendicular to each other. Then their moment of inertia, that is Ixx and Iyy, okay, when the moment of inertia, sum of the moment of inertia of y-axis and yz, xx and iyy will give you a perpendicular axis, okay, will give you the perpendicular axis in the vertical direction, which is okay, perpendicular to the plane as well as to the other two axes, that is called as IZZ. Okay, as you can see in the formula, this here IZZ is equal to IXX plus IYY. When it is possible, when the object and the axis lie in the same plane and these two axes meet at the centroid of the object and they are mutually perpendicular to each other, then summation of the moment of inertia of these axis will give you the third axis, that is IZZ. You can calculate the moment of inertia of the third axis. Okay, and this IZZ is called as polar moment of inertia. Okay, we'll study in the next uh, slide what is polar moment of inertia in. So it is here polar moment of inertia. The polar moment of inertia of a body is the moment of inertia of the body about the centroid axis, as I said, about its centroidal axis, okay, which is perpendicular to the plane. This is your plane, okay, and it is perpendicular to the centroidal axis of the plane, like this. So that axis, okay, will give you the some moment of inertia, right? That is called as polar moment of inertia, IZZ. Okay, understood. Next is radius of gyration. It is the ratio of moment of inertia upon the area. The square root of ratio of moment of inertia to the area is called as radius of gyration. This is a mathematical form definition. The radius of gyration of a body is a distance from the axis of the reference where the whole mass is assumed to be concentrated, not so as not to change the moment of inertia about the given axis. So the radius of gyration is represented as k. Okay. Okay. Here we will end the first part. We will start with the second part in the next class.